The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Today I'm going to present part of my PhD thesis, which I did with Professor Majid Youssef at Western University. It's like a rehearsal for my defense on Friday. And I'm going to talk about only the part related to the fire-damaged performance in RC frames. The outline is, I'll start by an introduction, a brief introduction. Then I'll talk about the analysis procedure, some validations, the proposed method for engineers or researchers as well, if they want to use it, and some conclusions and summary. In this presentation, I'm not going to go in details because there are lots of calculations involved, lots of programming. So I'm just going to talk about the concept and how we are analyzing full frames using simplified methods. Why do we need to study the performance of structures after fire? Like this is Dubai in the New Year's Eve, and everyone was gathering there to celebrate the New Year next to Burj Khalifa, the highest tower in the world. And before 2 hours of that, a fire happened in the Address downtown hotel, which is the most prestigious hotel there as well. And they have state-of-the-art technology in preventing fire and distinguishing it if it happens, but they couldn't with all of the technology. So the fire kept going for hours. The fireworks started as well, so half of the people were watching the fire, half of the people were watching the fireworks. Fortunately, there were no casualties, but we need something to assess the performance of this tower after the fire. So we intervened. It's not for that, but we can use our method. So our main objectives are to propose simplified procedures to determine the maximum temperature distribution after cooling, after going back to the ambient temperature, and to investigate the stress redistribution that takes place in reinforced concrete frames after the fire, and to evaluate the residual capacity, stiffness, and deformations in all reinforced concrete members that were exposed to fire. So the main assumptions are, we use the ASTM for now because it's the basis that we are developing our procedure for, and maybe later we'll extend it to consider the natural fire. So during the heating phase, we consider the ASTM E119, but for the cooling phase, there is nothing in the ASTM, so we consider the ISO 834, which describes a gradual cooling period. We did the heat transfer analysis using finite difference method, and we considered that the thermal properties of concrete are irreversible. So once we reach the maximum temperature, they will be fixed because they change with temperature. So once we reach the maximum temperature, they will be fixed throughout the cooling phase. Plane sections remain plane up to temperatures of 1,200 degrees centigrade, and this was validated by Al-Fitiani and Dr. Youssef as well. Perfect bond between steel bars and concrete are also assumed. Spalling is neglected. So basically, we are mainly considering the normal weight concrete in typical applications. Geometrical nonlinearity is neglected, so buckling of columns is ignored or things related to that. Influence of tensile cracks on heat flow is neglected. So if you have some cracks, we assume that concrete cover is still valid. So the analysis procedure encompasses 3 phases. In the first one, we analyze the structural member before fire to determine its stiffness and capacity. And this is like a basis to compare the residual properties to the actual properties of the intact member. And then during fire, we need to consider the interaction between load and temperature at each time step. And we'll go through that in detail later. But in this case, we need to capture the maximum temperature reached, the load level caused by restraining thermal expansion, if there are restraints in the building, and to check if failure occurs. If the member didn't fail, then we'll go to the other step, which is studying it after fire, to determine the residual properties and the residual deformations. So this is a typical concrete section. We use for thermal analysis the finite difference method. So firstly, we divide the section into finite number of mesh elements, and we subject the member to fire from either 3 sides, 4 sides, wherever we want. And we apply the finite difference method, and then we can plot the contour lines. From there, we can take the average for each layer, and we consider that this layer has a certain temperature for concrete. But for steel bars, we take the exact temperature at the exact element that the steel bars is located in. And there are many methods, like in literature right now, that describes the actual temperature distribution in concrete beams or columns after fire, like the Wickstrom or Gao. There are many methods, but they describe these temperature distributions at the end of the heating phase. So we proposed a method based on an extensive parametric study to convert the temperature at the end of the heating phase to the maximum temperature reached after cooling. Because during cooling, temperature still increases inside the concrete as it transfers to both sides, to the atmosphere and to the core. So this is how we convert the section, the concrete layers. We know the temperature in each layer, and the steel bars will be converted into steel layers. And for the residual strains, so if we have a column before fire, and if we heat it, it will expand. After fire, it will contract a little bit, but because of the permanent cracks that may take place between the aggregates and the cement paste, there will be residual expansion, and this is called the free thermal strain. We modeled that based on the Eurocode model, and this is a typical thermal strain of an axially loaded, like a column heated from four sides. But if the column is loaded, there is another term called the transient strain, where the column will experience something different. It will contract depending on the applied load and depending on the maximum temperature reached. So we considered Terro model to describe that strain component after fire. And if we combine the free thermal strain and the transient creep strain together, we will get what's called the residual strain after fire. And this residual strain can be divided into two strain components, which are the equivalent strain, which is related to the actual deformation of the member, and stress-induced strain, which will maintain the equilibrium between the steel bars and the concrete. So let's explain it more. This is the initial condition, and this is what the column tends to be after the fire. Steel bars tend to go back to their original positions because they are metal, and metals restore their initial length after cooling. And concrete tends to keep some deformation due to free thermal strain and the transient strain combinations. However, what we see is something like that, because plane sections remain plane, and this is the uniform residual strain, and there are some residual stresses that keeps this shape. So after fire, the columns or the beams or any other structures have some stresses inside. So these equivalent strains are going to shift the load deflection curve after the fire, either to the expansion side if the column was not loaded before the fire, or to the contraction side if it was loaded after the fire, as we said, due to the effect of transient strains. In our model, or in our methodology, we categorize the structural members in any building into four categories: the unrestrained unloaded members, unrestrained and loaded members. Then we have the restrained unloaded members and restrained loaded members. So for each beam or each column, we can remove the actual joints and replace them with springs with either axial or rotational degrees of freedom, or stiffnesses, sorry. And we can obtain the residual stiffness for each column or each beam after the fire from the calculations. So to explain that more, if the column or the beam is unloaded and then we applied a temperature of, let's say, 500 degrees and a load of 100 kilonewtons, we can do that by many ways, either to apply the temperature first, then the load, or the load, then the temperature, or to do that in increments. So if we apply the temperature first and then the load, we will reach the same stress and temperature state at the end. But according to the strains, we will have free thermal strain first, and then the influence of transient strain will take place. So we reach a total strain at that point. However, if we apply the stress first and then the temperature, we will go in another path. So we will increase the mechanical strain first, and then we'll get some thermal strain, and the values are different because the member was heated after loading. And as you can see, the total strains in both cases are different. In usual cases, if we have restraint during fire, then we'll have something in between, because while the member is heated, it will push the joints and they will push back, so it will be subjected to more load. If it's subjected to more load, then transient strain will develop, and the transient strain tends to reduce the impact of fire, of the expansion. So it's something that needs many iterations, and we did a code to do that. So I don't have time to explain it in details now, but this is the concept. For validation, I just used this one for now, but we had many others. This is an unrestrained column by Chen et al. 2009. They tested columns of normal concrete for 2 hours and 4 hours with the FC prime of about 30, a field for 80, and reinforcement ratio of 1.4%. And as you can see, there is an expansion at the beginning after the columns were cooled down, and then the residual load deflection curve. Our model was capable of capturing the actual experimental results to a good degree, considering that this is fire. And what we did after doing all the numerical analysis and all the validations, we proposed some regression equations to determine the residual strength or the residual stiffness, the residual strains, residual curvatures in all structural members if they are heated from 4 sides or 3 sides, for different fire durations, different mechanical properties for steel and concrete, and for different restraining conditions, whether they are axial or rotational. So this is a simple equation. There are quadratic or equations, but this is one of them. So we have the coefficients here, we have the equation, go to the table and get the residual strength, get the residual stiffness, and so on. Now, what we do, what we are expecting engineers to do is, this is the important thing now. Suppose we have a frame which is loaded, and then fire happened according to any scenario. Like, let's say this scenario, the fire happened at the facade of the building, for example, and we know the cross-sectional dimensions of each beam and column at the sagging and hogging moments, or the ones that are exposed to fire. So what we need first is to get the restraints acting on each member first. So how do we do it? We isolate the column. For example, if we want the stiffness of that column, we isolate it from the structural model, which is already built in SAP or ETABS or any structural analysis software, finite element software. And we apply a unit load, measure the corresponding deformation, and from there we can get the stiffness of that joint. Then we apply the same unit deformation at the other joint, and we get the corresponding stiffness. And then we consider them as springs in series, and we can get the restraints acting on that member. The same thing for the beam. We apply a unit load at, let's say, of this beam at the left, and then at the right, then take the equivalent restraint. And because beams are subjected to significant flexure, we also consider the flexural restraint in the same way. Now, for the intact frame, this was the load deformation shape. And for the fire-exposed frame, that was the load deformation shape. So what we did, we analyzed the structure first without applying any influence of fire. And then we changed the stiffness, which is the EA and EI of the columns and the beams that are exposed based on our regression equations that we obtained from our analysis in the model itself. So any structure that is exposed to fire from 3 sides or 4 sides, we know how much it was restrained, we know its mechanical properties, we went through the equations, got the reduction in the stiffness, and we put it in the finite element software. The other members were not changed, so they stayed the same. And then we run the analysis again. For the residual deformations, we applied the residual strains or the residual curvatures as either temperature load or temperature gradient, which is an input in the SAP software, for example. For example, if we have an equivalent residual strain, we can use the alpha, which is the coefficient of thermal expansion of concrete, to get the corresponding temperature, because strain is equal to alpha times delta T. So we put the delta T based on the strain that we have, and similarly for the temperature. This is the normal force distribution before fire, and that was the normal stress distribution after the fire. There is a difference in the format because I did each one in a different time, so I forgot what was that. For the shear force distribution, it was the same. So this is the intact frame, according to the load that I showed you at the beginning. And this is the shear force distribution after the fire for the same load acting on the building. And for the bending moment, actually, as you can see there in that column, we have a significant moment on the column because all structural members are interacting with each other now. So the beam is affecting the column because it's expanding and there is a moment there and all over the structure. So this is the concept. I think engineers in this way can just compare the values from here with the residual capacity that they will calculate from our equations as well, the proposed equations, because we provide them with the residual capacity of each member. So if the members pass that residual capacity, then they are okay, the structure will stay. Otherwise, it may face some problems. In conclusion, we found that fire duration, member weight have the most significant influence on the residual performance of columns and beams and other structures. And we have developed a method to determine the residual performance of structural members after fire. And these are some of the references that we used in the model. And thank you for your listening. If you have any questions, please ask.